Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. We've got a long one for you today. We're going to look at the use of the 555 timer. Now, we're not going to go into the internals of the 555 timer. We're just going to look at the external circuit with the two resistors, R1 and R2, and the capacitor. And we're going to look at how we use those values to design a particular frequency and duty cycle for our 555 timer. Now, some of those terms seem foreign to you. We will be going over all the details in this video, so let's get started. Okay. All right, great. So 555 timer design. Okay, so what does a 555 timer do? So there's going to be a little bit of lecture notes here as we kind of go through this first one, since we haven't seen this before. Let me just turn this just a little bit in there. There we go. Maybe I'll be more in frame. All right, so basically 555 timer makes a square wave, and so it makes a square wave, and we can control the frequency and duty cycle to a degree. And the duty cycle is going to be greater than or equal to 50%. Okay, so let's look at a square wave. So those are all supposed to be the same size, just FYI. And so there are a couple of features here that we are interested in. And so first off, we're interested in the time it takes to make one complete cycle. And so this is called the period. And that gives us the frequency as 1 over the period. Okay. We also have this time. This is time high. So that's how long it's staying at its high value. And then we have this time. That's time low. Okay, so we have time high, time low, and then the period of the signal. Now you can see that the time that is high is longer than the time that's low, and so sort of those two go into the idea of a duty cycle. So what percentage of the total is time high is what we're asking for the duty cycle. So when we're looking at that duty cycle, we're looking at equals time high over the total period multiplied by 100. And that will give us a percentage. Okay, so just to give you some examples here. So here would be something that is about 25% duty cycle. And then here would be a 50% duty cycle. And then here would be a 75% duty cycle. And so all three of these we have to realize have the same period. So if I look at the period of these, they're all the same. So the only difference is how much of that period is high and how much that period is low. So all these have the same period and thus the same frequency. Okay, so let's go on to next bit here. So design equations. Well, let's take a look at the 555 timer. Okay, and I'm not going to care too much about what all these connections are, but I'm just going to show you how they're connected into the circuit itself. So basically you have two resistors and a capacitor connected to this ground, and then here is 5 volts. Okay, and then there's going to be a connection from each of these locations into the 555 timer. We call this one R1, R2, and C. So really that's all I want you to know right now. And if I look at these 3 components, so these 3 components allow us to design and choose the frequency and the duty cycle. Okay, so that's what we're looking at when we do this. So we get to choose the values for R1, R2, and RC, and that will get us the frequency and duty cycle. So let's look at the design equations. So given the insides of the 555 timer and the operation of resistors and capacitors, it generates a set of equations to allow us to design. And I want to just give them to you here. Now, don't worry too much about copying down what I write, because these are available all over the internet, so you can find them pretty easily. But I just wanted to kind of show them to you here as well. So F is equal to 1.44, and don't even think that I have these memorized, because I do not. R1 plus 2R2, although they're not terribly difficult to memorize if you wanted to. It's just I don't use them frequently enough to know them by heart. Okay, so that's the frequency. Okay, so that's one of the things we want to design for. And then we also have the time high and low. So time high is going to be 0.694 R1 plus R2 times C. And time low is going to be 0.694 R2 times C. And then the period is going to be 0.694. We can find this by taking 1 over F multiplied by R1 plus 2R2 times C. And so these 3 together, all the time calculations here, okay, and then they work to give us the duty cycle. And so if I take time high divided by the period, we can see that 0.694 and 0.694 drop out, C drops out, so we're left with R1 plus R2 over R1 plus 2R2. So it's R1 plus R2 over R1 plus 2R2. So typically, we can use these 2 expressions, the frequency and the duty cycle, and not worry about these times high and times low, which we might not really care too much about. We just care that the duty cycle is what we want it to be and the frequency is what we want it to be. And then we can use these to generate our expression. Now, we only have 2 unique equations here, and I'll show you that to you once we do an example. So we have 3 variables and 2 unique equations, so we're going to have to make a choice for one of our values when we do our design. Okay. One thing I want to point out to you is if we use the law of large numbers compared to small numbers here, what we can find is the duty cycle range. And so if I make R1 really large compared to R2, this right side of the equation basically means very little, so we can drop out, and it's R1 over R1, which gives us 1, which gives us 100%. Oh yeah, we have to multiply this by 100, right? So that would be 100% duty cycle. And if I make R2 very large compared to R1, we get R2 over 2R2, which gives us a 50% duty cycle. So that's where we get our range. So if R2 is really big, we get a 50% duty cycle. If R1 is really big, we get a 100% duty cycle. Okay. All right, so essentially we're using these equations to generate the performance of this circuit. So at this point, what I kind of want to have you remember here is that this sort of vertical arrangement of resistor, resistor, capacitor is what is the external part of the 555 timer circuit to generate a square wave with a selectable frequency and duty cycle. And then the second thing is that these are the design equations, and then if we use these, we can figure out what those values would be. So let's do an example. So I have example. In this example, I'm going to choose that I want a frequency of 2 kilohertz, and I want a duty cycle of 75% or 0.75. Okay, so that's what we're designing for. So I can plug those into the two equations that I want to use as my design equations. So I'll use the frequency one, 1.44 over R1 plus 2R2 times C is equal to 2000. That's one. And then the second one is that R1 plus R2 over R1 plus 2R2 is equal to 0.75. Now I can solve and substitute and then solve again here, but you're always going to run into that you know two equations and you have three variables. What are our three variables? R1, R2, and RC. And so we need to choose something. And so I think the typical method for design is to choose a nice capacitor that you want to use, and then from there find out what R1 and R2 are supposed to be. But one thing to consider is current. So current should be managed. And so in this situation, we want current in the milliamp range. Okay, so if I want milliamp current and I'm dealing with a 5 volt source, so we got volts and we're going to divide by kilo ohms to get us into milliamps. And so we're going to have something in the kilo range. So I made a choice and I said, let's make R2 10 kilo ohms. Okay, so if I make R2 10 kilo ohms, that's an equation, that's unique, that's unique, that's unique. Now we have three equations and three unknowns. So I'm not going to do the substitution. I want you to use a system solver to solve this. And if you do use that system solver, you'll get R1 is equal to 20 kilo ohms. And you'll get C is equal to 18 nanofarads, or 0.018 microfarads. Okay, so that is our solution. And that's all there is. And so we found the values of the components on the external circuit that will allow us to run that 5.5 timer at 2 kilohertz and a 0.75 duty cycle. Okay, one more part to this. Let's go ahead and look at the simulation. Okay, so I took the liberty of building out the 555 timer. So here it is. This is the 555 timer. And you can see there's a couple more connections. I don't want you to worry too much about it. But we have 5 volts here connected to the resistor. Then there's a connection from the center of the resistor to the 5.5. Then the second resistor, R2. Then a connection, and then our capacitor to ground. Okay, so that's what we're looking at. So these values are 1K, 1K, and 1 mic. And when I did that and I made the graph here, this is a triggered oscilloscope graph, and we're looking at the signal here. So what I'm able to measure easily off this graph is the voltage and the time. And so we have a 5-volt signal, and I can measure the time it takes to do 1 full cycle. So 1 full cycle here will give me the period. And what's 1 over the period? The frequency. So we can check our frequency. And indeed, these cursors are really nice because I can drag them around and I can put them at the beginning of one of our cycles, and I can put the other one at the beginning of the next cycle. And down here at the bottom, they show us where they're at, but more importantly, they show the delta. So the difference between those two positions on this graph is about 2.14 milliseconds. And if you take 1 over that, that's the period. If we take 1 over that, we get the frequency of about 467 hertz. So this is generating or designing a 467 hertz frequency. Now we could also use this to generate the duty cycle, but I'm not going to go through that process. But we can measure high, and we can measure the period, and we can just do that division to figure out what it is. I want to try our example, and so I'm going to substitute for these values in here. So our R1 we found to be 20,000, and so 20K. Our R2 we set at 10,000, so 10K. And then our C we found to be 18 nanofarads. And so there we have 20,000, 10,000, 18 nanofarads, and I'll run it. Okay, and so now I can adjust let's see, where are we at here? Axes, voltage. Where do I have an adjustment? I thought I had it here. Oh, maybe I just have to go here now. It's single, trigger. Oh, okay, well, I think I can do this down here too. Sorry about this. I swear I had a control that allowed me to adjust this. Let's try if we change it. Okay. Oh, it's because it wasn't running. All right, there we go. Okay, so I love that you guys get to see me make mistakes, because like that's reality. I mean, I could have curated this, stopped this video and started it again and like, oh, Mr. Stanzik knows how to do it perfectly. But the reality is that sometimes we have to play around and we make mistakes, and it's fine. Okay. So I'm going to put my cursor here at the beginning of this cycle, and I'm going to put it at the beginning of the next cycle. And what we have is a full period. Now, for the big reveal, we go down to the bottom and we see that the period is about 500 microseconds, which corresponds to a frequency of 2 kilohertz. That's what we designed for. That's amazing. So it's working as we expected. Furthermore, we are looking for a 75% duty cycle, and just by eyeballing this, I can see that if we're not exactly on, we got pretty close to 75% right there. And so that's how I wanted to show you that we could design a 555 timer without knowing its internal operation, just knowing that we have R1, R2, and C, and we have some design equations that go with that, and we can use those design equations to generate the frequency and duty cycle that we're looking for. Well, I hope you found that to be a valuable experience, and I enjoy you participating in watching these videos. Appreciate your participation. My name is Mike Stanzik. This is Digital Electronics Classroom, and I want to wish you a wonderful day.